Hello and welcome to Neat AI. This one is all about the casino version of Blackjack, sometimes also known as Pontoon or 21. I wanted to focus on the impact of card counting and how, if combined with correct basic strategy and done correctly, it may lead to a good day at the casino. Will it start raining cash? Or will you go broke? We know for a fact that casinos don't like card counters. They're easy to spot because of their betting patterns and are normally kicked out immediately. So perhaps there's something to it. So I've decided to code up the game with all the normal blackjack options that you get in a casino, so you can stand, hit, double or split. Blackjack pays 3 to 2, the players can double after a split and are allowed to split up to 4 times in a hand. And then I'm going to have a small population of neural nets in combination with a genetic algorithm train itself on the basic blackjack strategy, which first appeared in the excellent book Beat the Dealer, which was first published in 1962. I'll then add card counting to the mix and see what kind of betting optimizations the network can come up with. So it's time to start coding, and I decided the first thing to do was create a class for the table, then build a class for a player object, create 2 instances of it, and label one of them the dealer and one the player. I'll need a shoe to hold the decks, and I'm going to populate this simulation with an 8-deck shoe. And of course, I'll need a class for the cards, which will be dealt to the player objects. All of that combined will be my complete object model, and I'll create a population of about 50 when I start training the network. I'll also plug in the neural network class I developed during a previous project, and they'll all play their own blackjack hands heads up against the dealer. So the fact that blackjack is beatable was proven in the 1960s. How to play basic strategy is well documented, and I wanted my neural nets to learn basic strategy as a starting point. Every pair of hole cards has an optimum action, depending on the face-up hole card of the dealer. So if your hole cards sum to 15 and the dealer is showing a 5, then you should stick. If they sum to 9 and the dealer is showing a 10, then of course you should hit. And as everyone knows, once you've mastered basic strategy, it will immediately start to rain money. You'll get richer than Scrooge McDuck, and bikini models the world over will want to be your friend. Okay, so let's train the network and see how it goes with learning basic strategy. I'm going to start with 50 dealer player card combos, and each generation will play 200 hands one-on-one with the dealer. The inputs to the neural net will be kept simple. I'll pass in the player hole card values, their total hand values, the dealer's face-up card, and a bias value, which is always set to 1. The outputs will be confined to simple player actions, namely hit, stick, double, and split. The fitness function, used to steer the evolutionary process, was linked to how close the actions of the nets mirrored the basic strategy for blackjack. So for example, if a player received a 15 and the dealer was showing a 5, then the correct action is to stick. And if the player chose this option, then its fitness would increase. Conversely, if the player has an 11 and the dealer is showing an ace, then the correct action is to double. Anything else results in the fitness of the player decreasing. At the end of 200 hands, the generation is finished and the fittest players identified. They then go on to produce the next generation of players through a process of speciation, crossover, and mutation. Normally, the mutation stage of a genetic algorithm simply means mutating the weights between nodes. But here it also allows for new nodes and connections to appear, which greatly increases the power of the network. And this cycle of speciation, crossover, and mutation repeats over thousands of generations and has the effect of steering the population towards increasing fitness and reducing the error. And this is the same approach I used in the Flappy Birds and Asteroids series. So applying this approach over thousands of generations, I'm able to monitor the fitness progression, and in spite of a slow start, it eventually starts to align with correct basic strategy. On the top I place the neural net of the champ from each generation. The 3 hidden node solution seems to be preferred, and for most of the training cycle it focuses on modifying weights during the mutation stage, but it gets the job done. So with basic strategy mastered, how does it fare against other playing styles? Published research puts some numbers on it, typically in the form of profit or loss per $100 bet. A drunk player, for example, who never hits, doubles or splits, will normally lose in the region of $20 to $25 per $100 bet. A regular player that plays a lot, goes off his hunches, maybe plays the lottery because, well, somebody's got to win, will lose between $4 and $5 for every $100 bet. So over 2,000 hands, the Blackjack bot achieved a score of losing 51 cents for every $100 bet, which is on par with the figure of 62 cents, which appears in the research. But to get the numbers into the green, we need to now include card counting alongside basic strategy, and also figure out the correct bet sizes to exploit any advantage we may have. So the steps for card counting can be broken down into 4 simple rules. First thing to do is assign a value for each card. All 10s, picture cards and aces have a score of 1. All cards valued 2 through 6 have a score of -1, and everything else has a score of 0. Rule 2 involves keeping a running count as the cards are dealt, which will tend to bounce around 0 initially, but will drift higher or lower over time as the remaining cards become saturated with higher or lower card values. Rule 3 is calculate the true count. And this is easy enough to do as it's simply the running count divided by the remaining decks in the shoe. And finally, Rule 4 is to vary your bet as the true count rises, and it's this part that I want my neural net population to focus on next. I wanted to figure out what my bet sizing would be based on the current true count. So I set up my population again, playing perfect basic strategy, and fed the network the true count at each stage of the game. Each generation lasted for 200 hands of blackjack, and the network could vary its bet size between $5 and $200 in an effort to maximize its fitness. At the end of each generation, it again would speciate, crossover, and mutate. And this is what it produced. I'm plotting the average bet size against the true count, and as the true count went from -6 to -1, the network has decided that betting the minimum was the best option, as expected. But as the true count went positive, it did something a little odd. Instead of just ramming all its money in straight away and betting the maximum, it instead slowly ramped up its bet as the true count increased. So I did some research and came across a simple formula for expected value, which is simply the true count minus 1 over 2. Plugging in some values for true count, we can see that when it's 0, our expected value is negative at minus 1.5%. When the true count is 1, then we have a fair game, but it's not until the true count approaches 2 that our expectation starts to move positive. Which is great, because it tells me why the neural net has evolved the betting pattern it prefers. When the true count lies between 0 and 1, it's close to a fair game, so it starts to increase the bet slightly. Between 1 and 2, its expectation has moved slightly positive, so it starts to ramp it up, and anything above 2, and it shoves it all in. So with basic strategy, card counting and bet optimization in place, it's time to see how they combine and what results they manage to achieve. I've got the AI to play 20,000 hands one-on-one with the dealer, and have plotted the profit per $100 bet against the number of hands played. And for the most part, it manages to stay in positive territory, albeit with a lot of variation in the results. It manages to achieve an overall win rate of 43.76%, and a profit of $1.09 for every $100 bet. So does it work? It certainly does, at least in theory.
I have been kicked out of a lot of casinos.
In practice, well, you'll have to make up your own mind on that. The experts over at Blackjack Apprenticeship sure make it look easy, but they are the professionals. Thanks for watching. Please like and subscribe.